Okay, so here is a rough prototype of a possible ventilator design. Starting at the business end here, patient end. This could be used with an ET tube or a mask if you can have a mask that fits well. This has both the inspiration valve and exhalation valve built into it here, so there's no dead volume in the hose. And this is a 0 to 20 PEEP valve. So this is what would go on the patient, or connect this to an ET tube. The pump works in combination with a standard BVM. This one is from a company called Laerdal. This is a unique BVM and particularly suited for this design because the valving is in, as I showed in the mask, not actually in the BVM itself, which lets you connect it to this custom T fitting here. So this is, of course, the connection to the mask. This is the connection to the BVM. Normal medical oxygen comes in through the green hose into the end. This basically uses all the same valving that is standard with the BVM. So the 3 valves on this end and the 2 valves up in the patient mask end are completely untouched. This is the standard reservoir bag that fills with oxygen. And so this whole system, the bag, the actual flexible bag, the BVM itself, the tubing, and the pump will all be filled with high concentration O2 for high FiO2 for the patient. The heart of the system is actually this is an inflator pump for rafts, or kind of inner tube inflatables repurposed for this. So what I've used is the external cylinder and really just the piston seal on the inside. So there's a custom piston in here, but I've reused the seal from the stock pump. And so this is similar to the designs we've seen where people are squeezing the bag, but there's a lot of issues with that. Different size bags, different tidal volumes. There's concern about actually fatiguing and wearing out the bags. So this system pumps and uses the BVM, but it actually doesn't inflate or deflate anything here. So this will, when it's running, you will see this stay full size, and I don't have any oxygen flowing, so you won't see the bag inflate. But the whole system basically is pumping the room air and medical oxygen into the system through a piston assembly that is driven by the heart of the driving system is a Ford F-150 windshield wiper motor driving a custom cam. And so the idea is that there'd be 3 different cams for 3 different IE ratios. In this case, this is the IE of 1:1. You could have a cam for 1:2 and 1:3, or 1:4 if that was desired. And then each cam has 3 settings within it. And so this is for 400 cc's tidal volume, 450 tidal volume, and 500 cc's tidal volume. That's kind of the range that's been recommended for use for COVID patients. So basically there'd be 3 cams, each with 3 steps on it like this, and that would give 9 possible settings, combinations of inspiration-expiration ratio, as well as the different tidal volumes. So let me plug it in here and we'll make it go. So the cam's a little rough at this point. There's some mechanism issues to work through, but you can see the basic operation. So a lot of the designs I've seen use either a circular cam or some other type of cam mechanism that really doesn't give you the controllability over the IE ratio, and so that is one of the key things about this design. This design uses absolutely no electronics, there's no sensors, it's completely mechanical. The only thing we're driving it with is a benchtop power supply, variable voltage power supply, which lets us control the breathing rate. And what you see here, this is a speed sensor. Here there's a magnet on the cam, and the readout is up here. And so this is breaths per minute. So that's 19 breaths per minute. And we can increase the speed here. Say, here we go, 27, 28. So this is what it would look like at roughly 30 breaths per minute. It's a really simple system, basically custom piston. We're using, like I mentioned, the stock piston seal and then the simple rod guide system, return spring, and then this cam follower here is a bearing that follows the cam. And the way you adjust which track it's on, so which one of the tidal volume tracks, is by the spring system needs to be improved here, but the way this works is that you can undo this guy just a little bit. This block slides out. There's 3 different slots, a little hard to see, but 3 different slots. There's 1 slot, 2 slot, and then there's a 3rd slot here, and these are at different heights. So depending on how you stick it on here, the cam follower goes in deeper or shallower to engage the proper track on the cam surface. So all you need to do is slide this guy on here. Easier said than done. Oh, yeah, have to undo the screw here. There we go. Get it into place like that, and tighten it down. And so now we'd be running on the 2nd of the tidal volume tracks. Reconnect the spring. I'll have a better way to do this, and then drive the system, and now we're going again. So this is kind of a rough model, but shows the principle of a completely mechanical. So one of the main design drivers here was to do this with as much off-the-shelf stuff as possible, not actually squeeze the bag, make it as simple as possible, and have it so there's no firmware, no electronics, there's no Arduinos in here. This is completely mechanical solution that gives you the bare minimum. It's obviously a ventilator of absolute last resort, but the principle is that it basically pumps the BVM without actually having to squeeze it. So we can use different BVMs. If we use, say, for example, an ambu bag, there's a way to do that with an ambu bag. It's a little bit of a hack, but I think it would work perfectly well. But anyway, it's a rough system, but I think illustrates one possible approach for doing a completely mechanical ventilator, but still have enough adjustability in both, in all 3, tidal volume, IE ratio, and breaths per minute, including PEEP valve, and of course you'd need an external filter, viral filter, for the exhale, the exhaust coming off the mask. But that's about the only piece that's actually not shown here is the viral filter. The rest of it is completely workable.